Hi, good evening, everyone. Okay, welcome back to Plan 252, Transport Modeling. Okay, can you open your camera, please? Okay, uh, this is our agenda for today. Okay, uh, we will have introduction to IFN transport, especially in the ideal traffic assignment. And then we will discuss about network flow identity, NFI. Yeah, the goal is to do strategic policy analysis. Yeah. And at the end of this lesson, you will have individual assignment. Okay, in Moodle in level 2, and then you will also have for the group next week. So you will have a project presentation. Okay. Okay, good. So let's start with our first part. I guess you can go to Moodle. There is a slide on policy analysis. Is that correct? Okay, I will share this. Okay. Can you see my slide? Right. So this is an introduction to what is called ideal flow network. So uh, in 2014, okay, at that time I was in the end of one project, okay, supported by DOST and I think chat. Okay. Uh, and then we have discussion, what's the next project? Okay. My team, one of the member, okay, Dr. John Lee, telling, "Oh, how about if we do random walk on network to solve traffic congestion?" Uh, of course, this was kind of joke, yeah, because uh, random walk usually used for financial and so not for traffic congestion. So I took the joke seriously. So I tried to investigate this and eventually discover what is called ideal for network, IFN. Okay. Uh, yeah, the team don't want to join because there's no more money on that. Yeah. So, but this is the beginning of, I did not realize that it took me like more than 10 years, yeah, all of this research on ideal full network. Okay. So, today I want to discuss the following topic. Yeah. So this is a kind of workshop, so I did not go to the detail yet on how to compute. That will be next time. Okay. Today is just an introduction. Okay. So we will discuss what is strongly connected network pre-magic. These are the main two jargon that you need to remember. Okay. And then we will show you a simple baseline scenario and alternative scenario. Okay. And then you will practice. Okay. You will practice in the website and to compute this, all of this. So the stochastic matrix, the ideal flow, the congestion, and the performance. Okay. And you will see several advantages of IFN later. Yeah. So let's start with what is called transportation network. Okay. So look at this network in the left and the right. Okay. So the network in the left is not transportation network, while in the right, yes. Why? Can you check? Look like the same, but they're not. Okay, so the left network here from A, B, C can go to D, E, F, right? But cannot come back. So this is not transport network. You can go from your home to certain place, okay, but you cannot go home. So, okay, so characteristic of transportation network is what is called strongly connected network. Yeah. So that means from any point you can go to any other point, and you can go back home. Okay. So the jargon, this is not me who create. So in graph theory, this property is called strongly connected network. Okay. So the network in the right here is strongly connected. Okay. Well, in linear algebra, okay, the matrix with the same property, strongly connected network, it's called irreducible. Okay, so this is in mathematics. Okay. Now, if you have transport network, yeah, I just draw it this way. Okay. So in each node, the other characteristic is in each node, the sum of flow, yeah, is the same. Yeah, the sum of inflow is the same as the sum of outflow, isn't it? What's the meaning? This is called flow preservation or conservation. There is no intersection that will suck the vehicles, isn't it? Yeah. So there is no node that actually will absorb or generate any flow. Okay. So this is the property, yeah, which is called premagic. Yeah. So how are we going to see this is premagic? Yeah? You take the flow. Okay, this is, I just put it simplified. Okay, so this is 2, 2, 2, for example. Yeah, and so on. So if you sum to the right and then you sum to the bottom, yeah, so the sum of each row and the sum of each column, you see the pattern here. Yeah, 8, 3, 3, 16, 12. Can you see? This will have exactly the same pattern. Yeah. So the sum of row, yeah, is exactly the same as the sum of column. That is the characteristic of flow preservation of premagic matrix. Okay, so can you remember the two jargon? Irreducible, strongly connected, premagic. Yeah? Okay. Okay, next. Now, uh, let's do it manually. Okay. Say if you have any network, okay, which is strongly connected, and that's the basic, okay, then you can create what is called ideal flow network easily. Yeah, say for 5 nodes or 6 nodes, up to 7 nodes, you can still do manually. Okay, so you can try by yourself using paper and pen. Okay, so the step is simple. First, you have any node as origin, so you set any flow. For example, I set 100, yeah, to one node. And then check, yeah, if the node have only one in edge, yeah, and one out edge, okay, that means the same amount of flow, right? Because premagic means the sum of inflow must be the same as outflow. But if they have more than one in edge, you sum all of in edge. Okay. And then when the node have more than one out edge, okay, then you distribute this flow based on certain probability distribution. Okay. So the probability distribution you can set as input. Yeah. So if you don't know, there is a theory called maximum entropy that can help you, okay, to set up the probability distribution. Okay, so that means if you don't have any information on the probability distribution, based on maximum entropy, then you will set up as uniform. Yeah. So now once you put all of this flow, okay, and then you can divide, okay, with the minimum flow, or any statistic of the flow. I will give you examples so that you will see. Okay. Say I have this network, 5 nodes, I don't know how many links here. So I set up here 100. Can you see? Okay. Now in node 1, okay, in node 1 in here, you divide, because I don't know the information on the probability distribution. Let's assume this is uniform. So 50-50, right? Going in is 100, so divide by 2, 50-50. Now we in this C here, in node 2, divide again by 2, right? So this input is 50, and then divide by 2 become 25, 25. Up to here, is it clear? Yeah. From here, you go to D. What happened to node 3? The 25 divided by 2 become 12.5 and 12.5, isn't it? Okay. And then in node 4, oh, there is only one link in and one link out, then continue, the same amount. So this is ideal flow network. In this drawing, this is already ideal flow network. So because ideal flow network is actually a relative flow, okay, relative flow, that means you can divide by the minimum or the maximum or the average, okay, or the sum. It's okay. Any statistic, of this. Say, for example, I divide by the minimum, it is 12.5. Then I have this another equivalent, IFN, which is all integer. So nice, isn't it? Okay, you have IFN, ideal flow network is basically a rational number, so you can always get integer now values. Sometimes numerically it is difficult to get. If the network is very big, so the value to get integer is difficult. But theoretically, it is possible to get integer number because they are relative low. So, any question about this? Do you want to practice? So, I have two scenarios here. This is your practice today. Okay. This is your practice today. So, I have two scenarios. This is the baseline scenario on the left. Okay. And then this is the alternative scenario on the right. So what's the difference? Okay. Exactly the same except this lane. This is 2 lane, in here is 3 lane. Can you see this? Okay. So the number here with the bracket, that means the capacity, relative capacity in terms of number of lanes. Okay. So I will explain and then you will practice. Is that okay? So first, we need to set up the scenario parameter. Okay. So the capacity per lane, I set up here 1,800 PCU per hour. This number comes from heavy capacity manual. Okay. So total demand we set up 17,500. This number comes from survey. Okay. So let's simplify it. So maximum speed is 40 kilometer per hour. All links the same. Okay. And then the link length is also simplified 1 kilometer. Yeah? So this is this condition is called SLC, steady link characteristic, yeah, constant. So this is earlier number. Say A, D is one lane, isn't it? Okay. A, B is one lane, B, A is one lane, and so on. So we put that into matrix. Okay. So this is the matrix that I draw based on this drawing. Is it clear or not? So if you have A, D1, then you will put here, A to D1 there. Okay. So this is the number of lane per direction. Yeah. So because the capacity, so this is C relative, yeah, capacity relative, relative capacity. Now the absolute value, okay, the C absolute, okay, APS, yeah. Of course, multiply, say one lane multiply by 1,800. So this is the actual number. Up to here, is it clear or not? Okay. So all you need to do is just input this one. Okay. You just need to input this one. Yeah. C relative. Okay. And then input the value here. Yeah? This assumption you need to input. Okay. And after that, you can calculate the stochastic matrix. Yeah? How do you calculate stochastic matrix? Easy. Yeah. So if you have the capacity matrix like this, okay. So 1 plus 1 is 2, right? So the total is 2. Now 1 divided by the sum in here. So you will get half, isn't it? Okay. So the capacity matrix, okay, you get the sum on the right, and then you divide this value with that sum, you will get what is called stochastic matrix. You see, or not? Yeah. No need to worry. Later we will practice. Yeah. In fact, I already create a program for you, so you don't need to compute this. Yeah. But if you want, we can practice in Excel. Yeah. Now, how to compute the ideal flow network? Yeah. Ideal flow network, okay, by definition, yeah, is the limiting distribution. So there is a limit, yeah, of relative flow in a simple strongly connected network, subject to constant of the flow conservation. Yeah, so it must be pragmatic. Yeah, so this is a steady state solution. That means theoretically correct. Yeah, so this is based on Markov chain and maximum entropy. Okay, so in the future we will practice how to calculate this steady state solution manually using Excel. Yeah, but at this point I give you the program so that you can directly use. Yeah. Okay, this is the computation in Excel if you want to calculate. Yeah. So from the stochastic matrix, okay, you minus with the identity matrix, okay, and then you set up this kind of optimization, yeah, so that total is the same as total flow, okay, and then you want to get this pi here, yeah, you want to get this pi. Okay, the solution of this optimization is this matrix. Yeah, yeah. This matrix is just a matrix. Yeah, of stochastic matrix transpose minus the identity matrix. J here are the 1, 1, 1, 1, 1. Okay, transpose mean horizontal, and this means you okay multiply this division in here. That means multiply with the generalized left in first. Remember last week you practiced already when we calculate regression. Yeah, generalized left in first. This is exactly that. Okay. Yeah. And then after that, you just calculate with Hadamard product, yeah, element-wise product. Then you will get the flow matrix. Yeah. Simple. So this is the example of that network. Okay. So we get calculated already the ideal flow matrix here. So you get this value. And look at the sum here. Yeah? The sum is 38. Yeah. So this is relative flow. Yeah. So, and then you said a while ago, our total demand is 17,500, yeah, not 38. So in that case, easy. Yeah. Once you know this relative flow, then you divide. Yeah. So 17,500 divided by 38. Okay. And then you multiply this scaling to the whole ideal flow, then you will get the absolute flow. Yeah. And look at this absolute flow, they are always pragmatic also. Yeah. The sum of row and the sum of columns are exactly the same. Yeah. Okay. And then from there you just divide. Yeah. The flow, this is absolute flow. Yeah. Calibrated already. Okay. And this is the absolute capacity. Yeah. This is just element-wise division. So this is called Hadamard division. Element-wise division. So 460 divided by 1,800, you get congestion. You see? Yeah. Flow divided by capacity is congestion. Okay. Yeah. After that, yeah, we can calculate once you have the congestion. Remember, yeah. So this is the initial data structure. So the connectivity. This is your input. Yeah? Three input you have. Yeah. Capacity matrix, a free flow speed matrix, and then the link distance matrix. These are the three input. Yeah. After that, the program will compute for you the stochastic matrix, the ideal flow matrix, and then compute the congestion matrix. Okay. After that, you will get speed. Yeah. This is the actual speed in the link. And then you will get travel time. You will get the delay. Yeah. You will get also the minimum travel time here. Okay. So how do you get this? Yeah, there are formulas that we can use. Yeah, so you can select either using grid shield. So these are the formula. I think we discussed this last meeting or two meetings ago. I forgot. Yeah, about traffic flow. Oh, last meeting you have assignment. Just right, the grid shield. Yeah. So these are the formula from grid shield, and then we also discuss. So this is using BPR. Yeah. These are the formula for BPR. Okay. Once you compute that, so you will get the travel time, T, you get the speed, yeah, and then you get the minimum travel time, and you get the delay. Okay. And we get only the positive value, yeah, the zero is not computing, yeah, only the positive value, and then you can get the average travel time, average speed, average delay, and so on. Then you can compare between baseline scenario and the alternative scenario. Okay, so which one is better? So that's it. Yeah. So this is what I want you to do for your real work project, yeah, in your group. Something like this. Yeah. And of course, not as small as this, but should be much bigger. Yeah. Not just six note. Yeah. Otherwise, it's not group project. It's just class practice only. Okay. So IFN have advantage, yeah, that it is a steady state solution, so similar to a queuing formula, which is also long-term stable, yeah, equilibrium. Okay, theoretically, this is very interesting because it's also based on Markov chain and a maximum entropy. Yeah, the flow are conserved. Okay, and then the data that you need to use is very minimum. Okay, in fact, you only need one link flow to calibrate the whole network. Okay, so based on this, you can, if you only compare network, you don't really need the data. Yeah, because based on this, you can do based on topography of your network structure. So many of you are urban geographer, isn't it? You study geography of the network, so this is very good tool, yeah. So, and next time we can discuss more detail that there are certain condition in IFN, yeah, that we can make it into Nash equilibrium the same as Pareto optimality at the same time. So in using the normal way of traffic assignment, this is impossible. Okay, but using IFN, there are certain conditions that make it possible. This is very awesome. Yeah, at least theoretically. Yeah. Okay, so now let's practice. Okay. Maybe after practice you can get more question. Yeah, you can practice this 1, 2, 3, 4, and then this one also. Yeah. So I'll give you the links. Moodle. Okay. The link is here. Can you see? Ideal traffic assignment. Okay. Can you go there? This one. So you will get this. Yeah, so this is my nice. So this is what you input. So I already inputted 1,800 here. Okay, you can select whether we're using PPR or using clean seal. Yeah, if you use clean seal, there is no parameter. If you use PPR, this is the default parameter. Yeah. In that slide, I think I use 15, yeah? Not 0.15. Yeah. So in here, you can generate random matrix. You can select how many number of nodes if you want. Okay, just check different number of nodes, then it will create random matrix. Yeah. So of course, this is an example so that you can see the format. Okay, the format is simple, isn't it? Just comma separated or space separated, but don't forget at the end of each row you put semicolon. Yeah, otherwise the program will not know which one is the row. Okay, so now once you create this relative capacity matrix, okay, so then you can also switch to random. So you can select random distance if you want, or you can set constant. Yeah, so you can set constant 2, for example, or 1.2. So I can delete that. There. Okay. Can you see? Okay. The same thing with the speed matrix. You can select as random between, say, 120. I think. I hope this is correct. There. So I can select at random. Okay. Or you can put as say 40. Okay, yeah. You can set up the three input, isn't it? You remember the slide a while ago? There, yeah. These are the three input, yeah, C, U, and L. Okay, and the three input must have exactly the same network structure. Okay, A is the network structure. That means adjacency matrix. Okay, let us check here. Yeah, if meaning the 0 and 1 of these three matrices must be exactly the same. Yeah, so you if not the same, you just click update matrix. Is supposed to get the same. Yeah, update matrix. So can you see? I have five here, five lanes. 9 lanes is so big, yeah. So let's make it 2 or 1. This one is like 1, 1, for example. Okay. So now if you click in here, I change it to 3 lane. Okay. When you update the matrix, can you see this is automatically update? Yeah. Because the network structure must be exactly the same for the 3 matrices. Up to here, is it clear or unclear? So once you input these 3 matrices, okay, and then you can set up in our example, we put total flow, isn't it? 17,500. So you type here, okay, and then you just click calculate, yeah. Okay, so then you get all. Yeah, you get the absolute capacity matrix, you get the link distance, flow, stochastic, yeah, the Markov equilibrium, ideal flow, congestion, minimum travel time, the travel time itself, in speed, delay. So you get everything. Huh? And then you get also the network performance, yeah, the entropy, the flow, congestion, travel time, speed, and delay. The summarize. Good enough? Okay. So can you practice? Or can you make this two network in terms of what you will do? You will create capacity matrix of baseline scenario and alternative scenario. Okay? And then just put there in that program in the web. Yeah, this is online, so as long as you get the link, so you can do it. Yeah. Even if you are using mobile phone, so you just scan this QR code, so you can always use this. Okay, try and I'll wait. So once you finish, you tell me, okay, if you have any question, if you have any comment, you probably will say why the result is not the same as in the slide. So I will explain why. Okay, okay. Go ahead. Capacity matrix.
Capacity map
Hmm.
of the
Hmm.
uh,
There are several things there that you need to make.
of the alternative scenario, sir.
A baseline and alternative scenario, both. Do you need more guidance for that, or you already know? I need your feedback, so I will not know if you understand or not. So
Sir,
hmm.
I got both the results for. I'm not sure if it's correct.
Okay, so show. You can
Yep.
share. Okay,
Um,
screen.
um, sure. Let me know if you see it.
Yes, I can see it.
This is the alternative scenario, and I'm not sure how to show the other one, so I just posted the
Okay,
copy pasted the
good.
base
So
scenario here.
can I see the top level?
Sorry.
No, can I see the
Ah,
parameter that
okay.
you input? Yeah. So this is the PPR on the
Ah,
top. Okay. So can you set this one 15 rather than 0.15? Okay. And then so this is the input. Is that correct?
yes, for the
Oh, this is the
alternative.
alternative. No, so because this is 3.
Yeah,
Okay.
this is alternative scenario.
Okay. Next, distance is okay. And then this is 40, that's correct. And then down, okay. Then calculate traffic assignment. Okay. Can I sit down? A little bit down so that I can, okay. Now you compare this with the slide. 1.8, wait.
Sorry.
Okay, good. That's correct. Okay. You can compare these values with the slide. Okay. Okay.
Um,
Yeah, so the flow is there, right? See, this is the flow 460. Is that the same? 460 also?
um,
Ideal flow.
uh,
Down
um,
there. Yeah.
here.
Yeah, okay. So you get exactly the same, right? And the
121.
congestion also you check is the same or not. Okay, this is 0.9 here in DE. Check there is the same.
Mm-mm.
This is
Okay.
alternative, so maybe different.
Ah, yeah.
You can change that on the
The
top,
three. Yeah.
the base values become
Yeah.
2, okay, and then update the matrix and
Ah,
okay,
update. Update and then
and then
calculate.
calculate. Then you're supposed to get the same exact.
Yep, 0.9.
Yes, okay, good. And then the now check the slide exactly the same or not with the result. Next one,
77.
next slide.
Um,
No, next. After this, there, this one, 6.4. Okay, so you can check the T0, V, and D. Okay, and then average travel time, average speed, and so on. So you can check there also. Okay, so supposed to be the same. Yeah,
here. Yep.
right.
7.81.
Okay,
Yes.
and then at the bottom,
The bottom.
okay, so you have the, I think below the travel time arithmetics, right? So 6.4. Is that
6.4.
same? Yes,
Yeah.
6.44.
Ah, okay.
Exactly the same, yeah?
Yep.
Yep. Okay. So, and at the bottom here, I will explain later. Okay, this is the NFI check. Yeah,
Mm.
this is later we will discuss about that. Okay. So, with that, all you need to do is just change the 2 into 3, then you get the alternative scenario, you get the result. and you copy and paste and then submit it as your assignment finished, right? Yeah. Yes.
Sir,
You need,
in the web in the mobile phone, I don't think it's updating my if I update the matrices, uh, the distance matrix and the max matrix doesn't update. So maybe that's not happening.
the mobile phone, what happened?
I'm missing in the app on the phone. And then I tried to calculate from my phone. And
Okay.
then
So
in the
still
in the
not good enough.
yeah, it doesn't update whenever I try to update the distance matrix and not speed.
You need to update the matrix.
Yeah, it's not updating.
It's not updating.
It's not, yeah. So maybe it only works in the
Okay, I'll check
in
the
the
mobile version. Yeah. Um, Thank you. Thank you for the feedback on that. So, but on the desktop is fine. Okay. But that's exactly the same program. I don't. It's just the formatting is different, but exactly the same program. So it's supposed to be the same. Okay. Is this clear or not? For simple matrix, you can use that. Okay. Okay. So I want to make sure everyone understand how you compute, and is there any question, any comment? So go ahead, please, or any discussion about this. So how is this useful for you? That's the question. Maybe you will say, oh, this is a matrix. I don't know how to put a lot of zeros there, right? And no worries, okay? This is just a way to compute, okay? In real, you will use, okay, I will share the screen. Okay. So you go up here, okay, and then click next. There. So in reality, this is what you will use. Huh? Okay, for the real project, this is what you will use, not the earlier. Yeah, this one is the how to compute inside, right? So in reality, this is what you will use. So you have a map. So you go to OSM website. So here, so this is example near UP campus. Can you see? Okay. So can you see that every time I move here, these numbers here are changing. Okay. So you go to your own project. Okay. So you go to your own project where I don't know. So you decide your own project, isn't it? Okay. Say, for example, I set here. Okay. So all you need to do is just copy and paste this one. These four numbers. Okay. Into this bounding box here. Okay. And then you can set this one. Yeah. Okay. And then click download. Okay. So if you click setting here, this is the default value. So you can change this value. Yeah. I put here 1,500. If you want to change it 1,800 is up to you to decide. Yeah. So you can also simulate how you compute this. Okay. So and then just compute. Yeah. And these are the display network. So if you want the UP part, I think I have it here. There. Okay. So if you have, this is the UP campus a while ago. Wow. Right. So you can zoom in. Okay. This is the circle, isn't it? You see. If you zoom in, zoom very detailed, okay, you will see this is actually a network with numbers. This is the node number. This is the link number. Okay. So then you can select the action. So you want to find the node, you want to find the links, you want to find shortest path. Okay. Okay. You can also select what the capacity, distance, maximum speed. These are the three input, isn't it? Okay. So the program computed automatically for you, for the baseline scenario. So your problem is to create the alternative scenario, then you need to do it manually. You can use QGIS and so on to modify this. Okay. So the baseline scenario, no problem, but for the alternative scenario, you need manual modification. Is that clear or not? Okay. Once you have that, so let me compute. This is very long. Let me draw a simple network here. Okay. So because the UP campus is very big. Okay. So this is based on this paper. Simple network like this. So for the link capacity, you can see this is the distance and this is the maximum speed. Yeah. And then instead of matrix, we use node and link. Yeah. These are the meaning of its numbers here. Okay. So then you can select a model. So in here, ideal flow network, of course, the default. Okay. Say you don't want the ideal flow network, you can use the all or nothing. You can use capacity restraint. This is the traditional traffic assignment. Okay. So you can also set up the real world data. You can also set up your OD matrix if you need. Okay, so for comparison. Okay. And then the value of the model you can select. Yeah, green shield. In here you have even modified green shield. Okay. And the PPR or Y3. This one's supposed to be 0.15, isn't it? And then the value, I think you don't need to change this one. If you are using value of PCU per hour, okay, one for the link capacity, or if your link is actually number of lane, then you need to use this. Yeah, depending on what is the meaning of links there. Okay, and these are the other model. And if you need GIS converter, is already here. So yeah, again, the link and node, then you can get into GeoJSON or zip file. Okay. Once you have that, so all you need to do is calculate. Then you can get the same, yeah, network performance, yeah, and then all the detailed links, yeah, maximum speed, the flow congestion, and so on. Okay. And you can export this into Excel. Good enough? Okay. And then you can calculate you can see the congestion, the travel time, and so on. Okay. So introduction only. So in the any question?
Question, sir.
Yes.
For our project in our research, our goal is to optimize,
Mhm.
and our goal is to optimize it, the network, correct? Our
I
goal is
cannot.
to optimize the network,
You need to
or
optimize the network. That means you have base scenario, okay, and then you create the alternative scenario that optimize the network. Okay. For your project, you can use this, no problem. Yeah, so I mean the software is already there for you. If you dare to use Python, okay, that is exactly the same. I think here in GitHub. Yeah. Say for example, oh, it keep running because this is web version, so the number of nodes is limited based on your hardware. It's not my hardware. This is the based on the browser, right? So then if you have a problem with because your network is very big, for example, then you use Python. So this is open source. The code is there. Okay, you can modify on your own. So it's public. Yeah. Yeah. And the documentation, I guess, in here. Yeah. So yeah, this is how you run in the Python. Yeah, you will get similar. Okay. And this is the result if you download, yeah, more complex. And you can see the name of the road. So, and then you can zoom in and zoom out. Okay. And you can define the scenario. Uh, you check the documentation more detail. Yeah. And then you can calculate, yeah, for each scenario. And you can calibrate using certain data. Okay. And you can find the optimization. Okay. So this is how you create the node file, the link file, and calibration, and so on. Yeah. Yeah. If you join the Telegram group of this, so you can get the documentation of the IFN transport on the web. Yeah. This one. It's already there. And there are many YouTube video on this, so there's no problem with that. Okay. Any other question? Okay. Now, can you practice before we go to the next one? Can you practice this? C1, C2, C3, C4. Yeah, this is the pair. Yeah, C1 and C2 are pair. C3 and C4 are pair. Yeah. So between C1 and C2, which one is better? Between C3 and C4, which one is better? And you just copy and paste. Yes, Ken.
Sir, correct. The ID basically we would choose the lower max congestion, correct?
Mm, the lower maximum max congestion. Yeah.
Yeah. Uh, Based on my I tried and the max congestion or is lower for capacity matrix 3.
Oh, okay. This is supposed to be the number. Is that correct? So if I draw, I will get this N1 and N2. Okay. What's the difference between N1 and N2? Can you see?
The difference, sir, is with
Hmm. Can you see the difference?
The arrow from A to B, sir.
yeah.
Exactly. Okay. The arrow from A to B and B to A, isn't it? Okay. Wow. Everything is the same. Okay. Imagine you have a network. Okay. And then just one link, you reverse the direction. It seems like very small modification, isn't it? Just reverse one link only. Okay. You thought probably the same. The performance will be the same, but they are not. Okay. One is better than the others. Isn't that interesting? Okay, so you try. Which one is better, N1 or N2? You got the ideal traffic assignment a while ago, so you input it and then you calculate with the same numbers. Okay, so which one is better? Aren't you curious enough? If you don't practice, you will not understand. So you better practice so that you will know. And then copy and paste the result in a notepad or something, and then check the detail. Hmm? It's just 4 by 4, very simple, isn't it? You can even type this. Come on. Yeah, so this is my question, yeah. So which network is better? N1 or N2? Anybody can answer that? Yes, Justin.
I'm not sure with my answer, sir, but I'm basing it on the ideal flow, the difference between them. Uh, for network one, I think network one is better than network two.
Really?
Well,
Yeah, that's interesting. How do you say this is better?
I'm basing it on the result I got from the ideal flow matrix.
Uh,
Or is that a wrong assumption to proceed with?
Usually when you have a traffic network, okay, ideal flow is basically the load, yeah, the demand for each link.
Okay.
Oh, this represent the demand, okay. The capacity represent the supply, okay. The performance of the network is either you use efficiency, later we'll introduce, or you use maximum congestion. That's the
Ah,
performance, okay. From the congestion, you can practically calculate the travel time, the speed, and the delay. So these are the basic performance in the network. So then if you want to say, oh, my network is better, that means the average travel time is better or the speed is higher. Okay? It's not the flow.
okay,
So
sir.
the flow is only one side. It is the demand side, right? So
Okay, sir.
if you talk about capacity, it's only the supply side. So uh, you need to combine the two, yeah, supply and demand to get the price. Yeah, in economic you get the price. In transport we get the congestion, yeah, or the travel time.
Okay, sir.
Clear? So which
Yes.
one better in that case?
Uh, the travel time I got for network one is 1.7921, while for network two it's 1.7813. So it's network two.
Network two is better, right?
Yeah.
Yes.
Yeah. Two
Yeah,
has a,
maybe you get different numbers because assumption is different, right?
yeah, yes, sir.
Yes, yes. So, but if I compute using this assumption that I set in here, okay, so I set 6,000 vehicle per hour. You can also set the same if you want. Okay, and the flow, interesting, yeah. The flow is different, right? Just change one link here. The flow is totally different. It's not the same. Yeah, and then congestion is also totally different, isn't it? And in fact, the maximum congestion also happen in different location. Yeah, yeah. This is 95. In here is 92. So, network two is clearly better, isn't it? In terms of what? In terms of travel time is better. Yeah. In terms of speed is also better. Yeah. In terms of maximum congestion is also better. Yeah. In terms of efficiency, this is also better. Yeah, this is the efficiency, the far pi. Okay, so but in terms of average congestion, 37, the same. Yeah. If you use the arithmetic average congestion, this is worse. Yeah, network two is worse. If you get the average congestion only. But the other indicator represent that this is network two is better. Okay. So my question is, yeah. Okay. I want to introduce you with certain notation so that uh, you probably need to remember the notation. Is that okay? Okay. So I use kappa here, K, yeah, kappa, represent the total flow in the network. Yeah. Okay, I use C tilde here, represent the total capacity in the network. Okay, and then I use this Greek character var pi, variance of pi here. Yeah, this represents the efficiency of the network. And the last one, okay, this one, this is called Z in Greek letter Z. Okay, this represents the maximum congestion. Now, if you want to compare scenario, right? You have baseline scenario and alternative scenario. So say the baseline is K1, yeah, kappa 1, yeah, and then the alternative scenario is kappa 2 here, right? When they have the same flow, that means the ratio is 1, isn't it? Is this clear or not? If you assume the two alternative, yeah, scenarios, yeah, the baseline and the alternative scenario, they have the same demand, right? So in that case, the ratio is 1. Is that correct? And then look at the number of lanes. They are also the same, isn't it? So if the number of lanes are the same, then the total capacity is also the same, isn't it? So then the ratio of the capacity is also 1. Is that correct or not? Huh? Okay. So the efficiency is not the same. Yeah. And the maximum congestion is not the same. Okay. But, okay, I took the ratio here. Yeah. You compute by yourself. You already computed, right? Okay. I took the ratio here. Say ratio of efficiency, and then this is the ratio of maximum congestion. Yeah. I get 1 point something and then 0.9. Interestingly, you try using your Excel or calculator, you multiply these two numbers. Amazingly, exactly 1. Amazingly. How can it be? Right? And not only that, okay, you compute this with the caret here represent the arithmetic congestion, average congestion. Okay, the G bar here is the capacity weighted average congestion. Okay, so the program is already have all of that. So you just divide. Okay, so this is represent a uniformity index. Yeah, congestion uniformity index. Yeah, so this is an indicator to represent, okay, which part of your network is actually have a problem. Is it low capacity, small local network, or the arterial network? Okay, the big capacity one. So imagine that now you have the tool, very simple tool, okay, and you have very simple way to compute, okay, an indicator. You can diagnose. You become a doctor, okay, that can diagnose what is the root of the problem in my network. Yeah, based on very simple indicator like this. Is this something interesting for you? Huh? So we are talking about macro level, a strategic level. Okay, in this NFI. Yeah, this is talking about strategic level. The ideal traffic assignment a while ago is down to the operational level. You have the actual network, isn't it? You have the actual network, you get the matrix you put there, okay? And then you will say, oh, then I can get these values, okay? But imagine you don't have the network yet. Yeah? For next week, you need to present your proposal, isn't it? Okay. So in the proposal, you probably don't have the network yet. That's fine. Okay. But you need to have a strategy, isn't it? Okay. You have the base scenario. This is my area. Okay. Then you will say, this is my proposed strategy to solve this problem of traffic congestion. Okay. So then the NFI, yeah, the network flow identity, will help you to tell whether your strategy is actually feasible or not. Yeah. Is it possible or not to do that strategy? You have the tool to check. Okay, your desire is actually feasible or not, or it is impossible to do it. Okay, number one. Number two, say your boss, yeah, the politician talking about, oh, I want to have like this policy. Then you can check using this simple formula whether what he want or she want is actually feasible or not. Okay. In fact, you can later, at the end of this lesson, you're supposed to know how to design strategically, yeah, with numbers to set up your goal. Yeah, this is what I hope you can present next week. Okay, that this is feasible or not. Okay, let me start with a simple. Yeah, this is. I hope this is the motivation of that. Yeah, so network flow identity is very general formula. Yeah, kappa is equal to C. This is the total capacity. Okay, var pi times Z. You don't like Greek letter, you can write it with your own letter. Yeah. Usually in my paper, paper and pen. Okay. I usually use K, C, W, and X. Yeah, just to make it simple. So what is the meaning of this? You have the total demand in the entire network of your study area. Yeah. Kappa here is the total demand of the study area. Usually you know, right? Okay. And then C here is the total capacity. Again, these two usually you know. Yeah. What you don't know is the efficiency. Okay. And you want to know the maximum congestion. But maximum congestion is something that you set, isn't it? Maximum allowable congestion. So this is a policy variable. Can you see this? Okay. So then all you need to compute is only the efficiency. Yeah, the var pi here. Okay. Let me show you more detail a little bit. Okay. What is total demand? Okay. You have the ideal flow. Okay. You sum all of the flow, all links within your study area. That's kappa. Okay. If you did not have the network yet, you cannot compute the flow yet, you can set your kappa. Right? Or you get the data from the previous network, then you get the kappa. Okay. Next is the total capacity. Yeah. So total capacity, you can use number of lanes. Okay. But it's better if you put it into the actual flow. Yeah. So in PCU per hour or vehicle per hour. Okay. So this is just the sum of total capacity. Yeah. So important, this must have the same unit as total demand. Yeah. So this is PCU per hour, then this one is PCU per hour. This is passenger per hour, this one also passenger per hour. Okay. If you calculate using for logistic, you use ton per kilometer per ton kilometer per hour. That's your unit. That's fine. So you use exactly the same unit. Is that clear or not? Okay. The unit must be the same as demand and supply. Yeah, have the same unit. Okay. Next is congestion. Yeah, congestion a while ago we defined as flow divided by capacity. That's simple. This is unitless because they have the same unit, so congestion is always unitless. Clear? Okay. So this is the average congestion. Yeah. So when we say average congestion, okay, we are not computing the arithmetic average. Yeah. We are using capacity weighted average congestion. Can you see this? So that means you have congestion is flow divided by capacity, isn't it? Okay. So, but the flow itself, okay, is congestion multiplied by the capacity. So then you divide. Okay. Remember, this flow is the total of flow is kappa. The total of capacity is C tilde. Oh, now I can get the average congestion as simple as kappa divided by C tilde. Is it clear or not? Okay. Then, if I know this, I can define a new parameter called var pi. Okay. What is this? This is just yeah, average congestion a while ago divided by the maximum congestion. Okay. So var pi is the average. This, remember, this average is not arithmetic average. Yeah. This average must be capacity weighted average. Okay. And then you divide by the maximum, then you get, okay, var pi. Of course, if you multiply, okay, var pi with the C, which is the maximum congestion, you get back the average congestion, isn't it? Yeah. I just cross multiply here. Clear or not? With that, we can now derive, okay, the NFI. Yeah? So G equal G, meaning that the average congestion, capacity weighted, are the same. Okay. From the left-hand side, you will see this is defined as var pi multiplied by the maximum congestion. Yeah, this one. Okay. On the right-hand side, what we have is actually kappa divided by the capacity. Yeah. And then you multiply across, you get the NFI, yeah, the network flow identity. Easy or not? Can you remember this? Easy? Any question up to here? So try to do in website a while ago, so you can compute. Yeah. So if I have this C1 and C2, yeah, and this is the efficiency. Yeah. C1 and C2, these are the efficiency. Yeah. So which one is better in this case? Which one is more efficient? Of course, C1 is more efficient, yeah. Closer to 100% is more efficient. Okay. Closer to 100% efficient. What is the meaning of efficiency here? Okay. This represents the behavior of the driver, you know. Okay. So if the route choice of the driver. Okay. So if the driver did not change their behavior, so the efficiency is still the same. Okay. So all you need to do is to check the efficiency of current, okay, and then compare to what policy that you want to change. Yeah, this is the pre-magic capacity of this capacity matrix. Yeah, this is the ideal, the lowest ideal. This is called cardinal network. Yeah, so this is the lowest cardinal, and this is the lowest pre-magic capacity. Yeah. So when you have pre-magic capacity, okay, this is the ideal of the same network structure, okay, then far pi, the efficiency will be 100%. At that 100%, what will happen? At that 100% efficiency, okay, so remember this one. If this is 1, what will happen? That means the average congestion is the same as maximum congestion. Can you see that? Okay. And what will happen if average congestion is the same as maximum congestion? That means the congestion is uniform, the whole network. That will happen when the travel time will be the minimum. Yeah. This is what I will say, I will call this pre-magic equilibrium, yeah, PE. Yeah. So at PE, at pre-magic equilibrium, okay, the user optimum, which is what is called Nash equilibrium, later on we will discuss more detail later, is exactly the same as the system optimal. Yeah, this is awesome. Yeah, but this is very difficult to get. Yeah, unless you design it for a new town, okay, then it's very expensive to get. But look at these numbers again. This is pre-magic. What's the meaning of pre-magic? The number capacity, okay, the number of lane going in is exactly the number of lane going out, isn't it? What does it mean? Balance. It means no bottleneck. Clear, yeah? Okay. So when your network have no bottleneck, okay, that is the ideal condition. So knowing the ideal condition, then you can design your network, isn't it? If you know the ideal, simple ya. To get the ideal is simply make it pre-magic balance. Then I know, okay, closer to that balance, better it is, isn't it? Okay. If you want to solve traffic congestion, you need to know what is the ideal condition. Okay. The closer to that ideal, the better. Okay. Oh, any question, any discussion about this?
Sir, question on efficiency. Does it mean that it's closer to, if it's closer to one, it means that it's closer to pre-magic? Is that
Yes, correct.
okay?
Closer to one is closer to pre-magic. That's exactly, if you look at the book of IFN, okay, the title is there is how far it is from pre-magic. And then that chapter is talking about far pi. Okay, so originally far pi was computed many different methods. Yeah, okay, because what we want is to go to find the matrix distance, kind of distance, how to measure the distance toward the pre-magic, because we know pre-magic is the best. We know that. Okay, so the question is how to measure that. Okay, so I use many different methods. I use KL divergence, I use Mahalanobis distance, I use many different methods. Yeah. Finally, settle with this one. Why this simple formula works? Yeah. In fact, not only working. Okay. This simple formula actually very awesome. Yeah, because this represents the efficiency. Okay, and then you can get the this network identity. Okay. Okay. So when you say, okay, seems like very simple, right? Okay. It's just network identity. Look at this deeper so that you will understand. Okay. With this, I can derive the theoretical numbers. Okay. If I have a policy, for example, called later on route diet. If I want to reduce the number of lanes, okay, if I want to reduce the number of lanes with the same demand, okay, demand is reduced, K is the same, okay, can I reduce also the maximum congestion? Can I improve the efficiency? No. The benefit of having or the advantage of having this formula is actually not on this formula, but on the ratio of this. Okay, when you start to compare different scenario, this is awesome. You know why? Because now you can only set the percentage. You don't need to know the actual total flow. You don't need to know the actual capacity. Imagine that. Okay. Even if you don't know the actual capacity, even if you don't know the actual total demand, okay, you only need to know the percentage going up or going down. Then you can set your policy. That's awesome, isn't it? Okay, so I did not make the slide yet so full, but I send you the paper in here. This one. Yeah, this is the tutorial anyway. Let's see. Yeah, this is the background. Can you see? Yeah. Yeah, this is the historical. You can just, this is a while ago. Okay. Right? Yeah, this is a while ago. This is the definition a while ago we already discussed. Yeah. And here I explain, yeah, in brief, yeah, that if you have your far pi index is 1 or 100%, okay, you will get pretty much equilibrium. Yeah. And this is actually very awesome. Yeah, if you combine this with a few more axioms. Yeah, so this is SLC, homogeneous links, and this one, yeah, IPLC. This is the active part of all the order pair is all the same. Then you will get, yeah, user equilibrium exactly the same as system optimal. Yeah, that means the price of anarchy is 1. Yeah, this is very ideal. Okay, yeah, but this is very difficult to get. Yeah, extremely difficult, I put here. Okay, so this is just theory. Okay, to be achieved realistically, this is very difficult to achieve. Okay, that's why very hard to get this. But yeah, this gives us a clear direction. Yeah, what is the ideal condition? Okay, at least you can use topological network design to do this. Okay, so far pi index, when you set it invariant, that means the efficiency is the same. Yeah, that means what? The driver route, the choices, yeah, the habits remain the same, right? That means what? That means this is a short-term behavior. When you change some things, yeah, say you have, say you widen or you reduce the lane, yeah, within the next 2 weeks or 1 month, driver behavior will not change. That short-term value, yeah. So, okay, then you will see the pattern. Okay, so the nice thing about far pi index is computed based on relative value of flow and relative capacity. Yeah? You don't need to compute the actual absolute value of the flow or absolute value of the capacity. Even with number of lane alone, you can get the far pi index. And this is the benefit of using this formula a while ago. Yeah. So this is an example. Yeah. So if I have this capacity matrix, okay, then I can calculate the ideal flow. Okay. And then I just divide. Okay. Right. 0 divided by 0 is still 0 by definition because this is automatic division. Okay, so then I have here 11 divided by 1, 8 divided by 1. So basically the F is equal to G, isn't it? Huh? Based on that, you can calculate the capacity weighted congestion. How do you get that? Easy. Okay, sum all of this, okay, 92, right? And then sum of all of this, and sum all of this, you get 11. So there you get the average weighted capacity weighted average congestion. Yeah, and then you divide, yeah, this number with the maximum. Where is the maximum here? Oh, 11 here, right? So you divide by maximum, so you get far pi index. Okay, so is it clear or not to compute this? Now look at this. I want to show you. Okay, now I scale this. Okay, instead of 111 like this is number of lane, right? So now one lane is 1,800. Okay, so then this is the number of, this is the absolute capacity matrix. Okay, when you sum, yeah, because this is 11 number multiplied by 1,800. Now the sum is now changed, yeah, not 11 anymore, now become 19,800. Okay, and then using this, you can calculate also the ideal flow. Okay, of course change. Because the unit is not the same, so you need to compute. Okay, then you compute the actual congestion. So if you use congestion, you need to use absolute value, yeah, not the relative congestion like this. Okay, so this is the actual congestion matrix. Okay, and if you look at the maximum is 61%, right? And then you divide again exactly using the absolute value. Okay, okay, the average is 46. It's not the same as the relative, but when you divide with the maximum, you will get exactly the same FARPA index. Yeah, awesome. Yeah. So whether you use relative value or you use absolute value, the FARPA index does not change. Is it clear or not? Yeah. So this is the derivation a while ago. We get this. Yeah. This is the network flow identity, NFI. Okay. Now, if you use ideal traffic assignment a while ago, okay, so then you will have better result. Yeah. NFI itself, then the equation here, this is general. Okay, you don't need to use ideal flow network to use network flow identity. You got it or not? Yeah. This is general formula for any network, any transport network. Meaning, transport network must be strongly connected. Okay, if not strongly connected, you cannot, of course. Okay, so as long as you have strongly connected network, this identity works. Not necessarily using ideal flow network. Okay, it's the same. So this is very general. Okay, but if you use ideal flow network, yeah, using ideal traffic assignment, okay, with certain assumption of Markov splitting, okay, then you will have a better result. Yeah. Only better result, that's it. Yeah. So let me give you example. Is that okay? Can you calculate the FARPI of this capacity value? What's the problem with C0 here? Can you see here? This in this column, the third column, okay, all zero. What does it mean? Okay, if a network have either source or sink, okay, they are not strongly connected. Okay, so you cannot compute. Ideal flow network cannot be computed because this is not transport network. Okay, when you have source and sink, either all one row is zero or one column is zero, okay, you cannot compute. Yeah, FARPA index is always zero, so useless. Okay, so remember, yeah, this is only work for transport network. Yeah, any transport network. Right? When I say transport network, means strongly connected. Yeah, when you go somewhere, you need to go to be able to go home. Is that okay? Now, based on this C0, okay, let's make it irreducible. That means I need to set certain numbers here, yeah, so that not all zero in the third column, isn't it? Let's try. Okay, let's play. Huh? Let's play with this. Okay, I have two simulation. Yeah, Based on this, I add in here 1 or I add in here 1. Okay, let's name this C1 and C2. Is that okay? Is it clear or not? Yeah, so the Z0 cannot be used, I know, because the third column is all 0. Okay, in that case, let's add a certain number of lanes in the third column, isn't it? So let's start with this one and this one. Yeah, so let's name it C1 and C2. Okay. Okay, and then what will happen? Yeah, we can compute, right? We can compute the ideal flow. Okay, basically the minimum ideal flow is the same as pre-matching capacity. Okay, and then you can compute now the var pi. Okay, so closer to 100% is better. Yeah, closer to 100. So that means C1 is better than C2. Yeah, as simple as that. Okay, but that have a lot of assumption behind. Okay. So if you use the SPAR pi index, yeah, so check, yeah, they are closer to 100% or not. Okay. But be careful. There are a lot of assumption behind when you use only SPAR pi index. Yeah. Don't use only SPAR pi index. That's dangerous. Okay. You need to see what is the assumption behind. Okay. If you notice, yeah, C1 and C2, they have exactly the same total capacity. Yeah, this is the assumption behind. You can compare because they have the same demand and they have the same capacity. These are the assumption behind. Otherwise, you cannot compare. You got it or not? Okay. When you want to compare only the efficiency, yeah, that means there are at least two assumptions that you have in your mind. Okay, number one, the capacity must be the same. Number two, the total demand must be the same. Meaning the demand and supply are the same. Only the efficiency change. Okay, come back to original network flow identity. Can you see this? Kappa equal to C, efficiency, and then maximum congestion. Now, if K, the kappa is total demand, right? If the total demand is the same, capacity is the same, okay? So what changed? It's only maximum congestion and efficiency, isn't it? Correct? That's why you can do comparison, okay? Because the two already set as the same. Okay, so be careful, yeah. When you only compare uh, var pi or maximum congestion, be careful. There are certain assumptions behind, okay, based on network flow identity. You need to set at least two of them the same. Otherwise, it doesn't work. Okay? So, let me show you, okay, what happened if you use C1 and C2, okay, and then we use 1,800 vehicle per hour, capacity is this one, right? And then now you said the total demand is 10,000. Yeah. So the total supply and total demand are the same. Okay. So in that case, you will get, because of the network flow identity, NFI, so then you will get the maximum congestion trade-off. Yeah. Of course, the more efficient it is, reduce maximum congestion, isn't it? That's logical, yeah. So if you want to reduce the congestion, you need to be more efficient. Okay. So how to make it more efficient? Remember, balance is the most efficient. Okay. So you change, okay, in many ways in order to make the network more balanced. Okay. So, for example, okay, using traffic signal. Yeah. So if you make the traffic signal adjusted so that the network more balanced, okay, the capacity depends on the green time, no? It's not just the number of lanes, right? The capacity depends on the green time. Now, if your green time is balanced, then it improves the efficiency. Yeah. The same thing, if your number of lanes is actually balanced, yeah, the total number of in lane and the total number of out lane is exactly the same, then it is very magic, isn't it? Okay. Then again, you can get a better result. Is this clear or not? Now let's simulate this. Okay. What happens if I don't set, yeah, if I don't set the same total flow, but I set the same maximum congestion. Okay, let's say in here, if you set the same total flow, then what happened? The maximum congestion change, isn't it? Now, what happened if we change, okay, the maximum congestion remain the same, the capacity remain the same, the efficiency change based on NFI, yeah, network flow identity. Of course, kappa equal to C, W times Z, the maximum congestion. So you will get, it can accommodate different flow. Yeah, the total demand change. Yeah. So with the same number of supply, okay, if you improve the capacity, the efficiency, of course, it can accommodate higher demand at the same level of congestion. Clear or not? Ah, simple ya. Huh? So, yeah, if you have the same level of congestion, yeah, the same supply, okay, but improve efficiency, of course, it can accommodate more demand. Right? So NFI, even though it's very, very simple, okay, when I open it for you, suddenly you start to see, hey, I can do a lot of this. Yeah. Okay. A lot, in fact. Okay. I will show you. So I can compute this, yeah, and different scenarios, okay, and compute until travel time, okay. Then you will see, okay, be careful, yeah, don't use only FARPA index alone, yeah, to evaluate, yeah. You only use this when you compare, okay, with what is called, in economic, we call it ceteris paribus. That means there are certain things that constant, you assume constant. So any model, okay, you need to state your assumption. Otherwise, it's dangerous to say something without telling the assumption behind. What is the invariance? I told you in the very beginning, right? The model represents certain assumption behind the invariance. You need to tell that. Otherwise, it's very dangerous to tell that, oh, my FARPA index is better. Well, FARPA index is better because you assume something. What is the assumption? Okay, so if the assumption is capacity is the same, okay, or maybe the maximum congestion is the same, or maybe the demand is the same. Yeah, so you need to tell the assumption that you use. Is that okay? So NFI only have 4 variables, isn't it? Total demand, total supply, efficiency, and then the performance index, which is the maximum congestion. Okay, so that means if you hold 2 constant, okay, one become trade-off. Yeah, if one up, the other one is going down, isn't it? Yeah, in the right hand side. Yeah, but if the kappa increase, okay, then one of these on the right hand side must increase. Yeah? Okay, is it clear? Yeah, so I put here ceteris paribus. Yeah, so the condition that the total network capacity and the demand is constant. Yeah, so if you improve the efficiency, then of course it will automatically improve the travel time, the speed, yeah, and congestion. Yeah, so this is one of example. Okay, it's called congestion rebalancing. Yeah, using NFI, yeah, using network flow identity a while ago, we can actually find the theoretical limits. Yeah. Up to what point I can, okay, reduce the number of lanes. Yeah. So what's the definition first? Number one, you need to define. Yeah. What is the definition of congestion rebalancing? Yeah. Suppose you have 2 networks. Yeah. So initial network is N1. Okay. The congestion is G1. Okay. And then you have a policy. Yeah. Something policy means change. Okay. So suppose you have a policy, okay, with the goal of this is the congestion rebalancing is the goal. Yeah. The same number of flow, kappa. Now you modify the first network, this is the baseline, into the new network, N2. Okay? Oh, this must be G2. So that the maximum congestion at the new state is actually less than the maximum congestion in the initial state. Yeah? So here, this is definition of congestion rebalancing. Yeah, the total flow is the same. Okay, you set a change in order to make the maximum congestion in the alternative scenario is better than maximum congestion in the initial. Okay, very general, isn't it? We did not tell what is the policy, it's just define it this way. Okay, so if you have that, for example, you can increase the capacity. You can increase the efficiency, right? Okay. So, or you can actually reduce the capacity by increasing the efficiency. Possible. Okay. So now suppose, okay, I want to do only, yeah, reduce the capacity. Okay. Look at this. This is important. What is important is actually in the mindset. Okay. Very, very important to change your mindset. What is the mindset that is wrong? You always want to increase the number of lane. That is a wrong mindset. Why? Okay. It's very easy to increase the number of lanes, but it's very costly, isn't it? What will happen? The whole area will become road. Your city is not livable city. Okay? Imagine your own house be demolished to become a road. What will happen to your feeling? Right? So, if you only have mindset to always increase the number of capacity, okay, that mindset need to be changed. Why? Because there is another way. Okay, you can actually reduce the capacity, improve the efficiency, and still get the same reducing the congestion. See? Okay. In fact, if you already exhausted all the way, yeah, improving efficiency, then you talk about increasing the capacity. Okay. But if your capacity or your efficiency is very low, why should you increase the capacity always? Just because one lane become congested. Okay. Okay. So question, how are you going to increase the efficiency? Remember, efficiency represent how the congestion become more uniform. Okay. One way, yeah, is actually improve the traffic signal control. Another way is actually using traffic information. Okay, so that they will go to other road that is actually less congested. Yeah. So you change the travel behavior of the driver. Is this interesting? Or maybe in fact, you can change using physical barrier. Yeah. You reduce the number of lanes, make it become a bike lane or a pedestrian friendly, or you make it into public park. By reducing the number of lane on the correct place. Remember, the key is actually the correct place. Yeah, finding this correct place is you need to find the optimization. Yeah, you can use ideal flow in this case. Yeah, but once you get the actual correct place, oh, this is the correct place that I need to reduce, okay, to make it balance, okay, then you can actually improve the condition. Okay? If your alternative scenario always increase the number of capacity, that is bad. Try to improve the efficiency first before you improve the supply. Is that clear or not? The change of mindset is very important here. Okay? Okay. So let's try, okay, to find the theoretical limit of congestion rebalancing. Yeah. So this is just a simple mathematics. Okay. So we fix the total flow, isn't it? Okay. So and then you transition the network from state 1 to state 2. Okay. The efficiency in the far pi 1 and far pi 2, and then you have maximum congestion 1 and 2, right? Okay, so then you just compare, right? So remember, kappa is the same. So in that case, you can get the C2 is equal to C1. Okay, so far pi 1 divided by far pi 2, and then C1 divided by C2, isn't it? So if you want to say, oh, I want to achieve congestion rebalancing, which define that maximum congestion in the second, the alternative must be less than the first one, then you put it in here, then you get this condition. Okay, this is the theoretical limit. Okay, what does it mean? Okay, meaning as long as your efficiency is still less than 1, okay, yeah, as long as your efficiency in the network, current efficiency is less than 1, then you can still improve by reducing the number of lanes, theoretically, yeah. We did not tell where. If you want to know the exact detail, you simulate using IFN a while ago, yeah. But theoretically, you can reduce the number of lanes, okay, based on the trade-off with the capacity change. Okay, so of course the theoretical limit means PE, yeah, pre-matching equilibrium. In this case, the lambda 2 become 1. Then C2, okay, become equal to C1 times lambda 1, far pi 1. What that mean? Yeah, it means the minimum new capacity must be at least as good as the product of the old capacity multiplied by its efficiency. As simple as that. Okay, if you know the efficiency and the actual capacity now, okay, then this is the theoretical limit, yeah, of the road diet, meaning you reduce the number of lanes. Okay, as long as your efficiency is not 1, you can still use this, you know. Okay, up to here. Is there any question, discussion, probably? Yeah. So be careful, yeah. So when you improve capacity, efficiency does not mean always improve travel time, yeah. Okay. So while the demand is constant, total capacity is not constant, right? In this case, because you change the capacity, okay, reduce, right? So in that case, improving efficiency in this congestion rebalancing is not always improve average travel time. Okay, so you can use the PPR formula or green shield if you want. So I use here PPR formula. This is the formula, right? Okay, so L here is the length. U here is the free flow speed, yeah, maximum speed. Here is 0.15. Eta here is 4. This G is congestion. And this is the travel time, yeah, in the link. Okay. So if you have this, okay, then you can use algebra. Okay. Now the limit become change, yeah. This is the theoretical limit a while ago. Okay. But now you have a new variable, yeah, omega. Okay, this omega represent the value of travel time here. Yeah. Because this one is exponent 4, okay, eta, exponent eta. So then if you want to include the travel time, if you want to reduce the capacity but still improve the travel time, then this is the theoretical limit. Awesome. This is awesome formula. Okay. Why? Because now you can reduce the capacity, the number of lanes, okay, but you can still improve the travel time, okay, using this formula. Yeah. So this is just the average of congestion. And then you exponent for each congestion, you exponent with eta. Eta is 4. Okay. And then you divide by the efficiency multiplied by maximum congestion. Okay. And then what you will do, you take the exponent of 1 divided by eta. Eta is 4, so 1/4 this one. Then you get omega. Once you get the omega, okay, you put it here, then you know the theoretical limits. Is this clear or not? Yeah. So, yeah. The main point of all of this formula is this, yeah. Yeah. It is possible to reduce the total network capacity, the supply, okay, and you still improve average travel time. The possibility itself is mind-blowing because that means, okay, you can start to optimize your network, not always increase the number of lanes. Change your mindset. Change your paradigm. You got it or not? Okay. It seems like, oh, it's just formula. No, it's not the formula. This is the theoretical limits, meaning the worst case. Yeah. The worst case scenario. Okay. So if you are still below that worst case scenario, that means you can still improve. So knowing the worst case, that means, oh, I still have room to improve. You got it or not? Now, any discussion? Go. No? So now we can use that formula, okay, of NFI, okay, to derive principles, to derive the traffic insight, yeah, or traffic principles, okay, as simple as this, yeah. If you hold two variables in the NFI as invariant, don't change, constant, okay, then you will see the trade-off, okay. Remember, NFI have four variables, isn't it? Total demand, total capacity, efficiency, and maximum congestion as the performance. Okay? So what will happen if you hold the total demand constant, total supply constant? Yeah? So if you have total demand and total capacity is constant, that means, okay, if you increase the efficiency, okay, the maximum congestion reduce. Okay? If you improve the and vice versa, of course, yeah. So if you want to reduce maximum congestion, so you need to increase the efficiency. Yeah. So, but if the maximum congestion increase, that means certain things in your network making the efficiency reduce. So it become a diagnostic tool. Okay, if you can see, oh, what happened? Why maximum congestion increased? That means certain if the constant, yeah, constant demand, constant capacity, and then maximum congestion increase. What does it mean? Certain efficiency is dropping, so become a warning for you, right? So you can monitor this, no? Okay, so this is one principle, yeah. Second, What will happen if the total demand we hold constant? The maximum congestion you hold constant also. Now you have the trade-off between supply and efficiency, right? If you increase the supply, of course, efficiency reduce. Hey, you increase the supply, actually efficiency reduce, not increase. Okay, and vice versa. Okay, meaning if you improve the efficiency, you can reduce the capacity by holding the total demand and maximum congestion constant. Wow. Right? Can you get the idea or not? Yeah. So if your efficiency is low, okay, more capacity is needed to maintain that maximum congestion. Yeah. Next, yeah, I'm just doing combination here. Yeah. Next, what will happen if your demand is the same, efficiency is the same? What's the meaning of efficiency the same? That means the habit, okay, the behavior still the same. Okay. What will happen if you hold total demand the same, the habit still the same? Yeah, the behavior does not change. Then, okay, if you increase the capacity, of course, congestion, yeah, maximum congestion reduce. Yeah, this is the usual, right? This is your basis to increase capacity, isn't it? Okay, okay. So you always assume the habit the same and total demand the same. That's why you increase the capacity. Yeah, this is the old paradigm, yeah, the old mindset. You are holding. Yes, cool. You want to ask a question, please.
I just have a comment on efficiency. I think in the Philippines, one of the efficiencies that we saw in EDSA is the inefficiency of the bus drivers. So they would often cause lots of traffic whenever they drop off passengers. Also, jeepney drivers, so they will block lots of traffic.
Yes.
And so what they did in EDSA is they created the barriers, and then this might have increased efficiency for the buses, and because they can't drop off just anywhere.
Hmm.
So these are policies. So I'm just thinking about
Yes.
efficiency, and this means actually more behavior of
Yes.
the drivers.
Efficiency is more behavior. That's correct. Okay. In fact, if you look at EDSA, okay, where the congestion coming from? The number of lanes suddenly changed, right? So the number of in lane, the total in lane and the total out lane are not the same. Okay, so that is one of the cause also, yeah, imbalance. So that's also efficiency. Yeah, not only driver behavior but also the lanes. Okay, and so when we say efficiency, many factors, yeah, not just lanes, also behavior and so on. So including traffic signal timing, yeah, those are also efficiency, you know. Okay, yeah, including information, yeah. So those are also improved in efficiency. Yeah. So when we talk about efficiency, this is still in the strategic level, right? So not in the operational or not tactical level. So that when we say efficiency is very general, yeah, can be any policy that you put, yeah, including behavior, including the lanes, yeah, including having a bus or public transport and so on. Okay, those are also efficiency. Okay. Next, what will happen if you hold capacity constant and maximum congestion constant? Okay, that means, be careful. I put here the pink. Okay, pink mean inverted relation. Yeah, green mean direct relation. Okay, so when you hold these two constant, the capacity and the maximum congestion constant, be careful. When that means now what you can do is no longer trade-off. Yeah, the pink is a trade-off, isn't it? Because one up, the other one down. Yeah, but the green one is both up. Yeah, or both down in the same direction. Yeah, that means if you improve efficiency, you can accommodate more demand, and vice versa. Okay, and if you increase the demand, automatically, yeah, in this example, we hold capacity constant, efficiency constant. If you increase the demand, automatically maximum congestion increase. Yeah. Logic, yeah. So interesting enough. Very simple formula. Okay. When we dig deeper, suddenly you start to see something is deeper than just the formula, isn't it? Okay. Now what will happen if we use the, okay, this is the last one, yeah. So if you hold the maximum congestion constant, efficiency also constant, yeah. That means increasing the capacity can accommodate more demand, yeah. Right? Automatically. So, yeah, with this now we can also have sensitivity analysis, yeah. So what will happen? Okay, so this is an example, yeah, with numbers. What will happen if we don't want to change the habit? Yeah, it's a short-term behavior. But there is a flux of additional 10% demand. Okay? And then there is also a breakdown, yeah, 1% breakdown in the road capacity because there is a road repair. Yeah. How much is the increase of maximum congestion? So we can compute, huh? Wow, you can predict using very simple formula, isn't it? Nice. Yeah. So all you need to do is just plug in the numbers. Yeah. So you see that we can increase. When the number of this ratio is 1.11, that means 11%. Yeah. Right. Increase around 11% congestion due to this influx of demand and broken road repair. Yeah. Very simple formula, but it's very useful. Yeah. To see the actual policy or actual impact. So what do you think? Okay, this is another example. Okay, say your group project may have certain district, yeah, small district. So you calculate the total capacity in your network. Say for example 25,000 PCU per hour, for example. Yeah, total demand is 15,000 per hour. Yeah, so and then you have the current maximum congestion, say 80%. Yeah, so what happened? You can calculate the efficiency, right, easily. Okay, say 75%. Okay, so and then for example, certain policy you lever, yeah, intervention. For example, oh, I want to do adaptive traffic signal. Okay, it will improve efficiency from 75% to become 85%. Then you can compute, yeah, the maximum congestion. Okay, from 80% now become only 70%. Yeah. Yeah. So this will reduce the maximum congestion. That means only in the certain critical links. Yeah. So Look at this. This does not change capacity at all. In this example, we don't change capacity at all. Yeah, the number of lanes still the same. So interesting. This is the basic of ITS, Intelligent Transportation System, isn't it? Okay, you improve the efficiency. Any comment, discussion, feedback? Do you get the idea or you don't get it? Formula is very simple, just K equal to C times W times X. Okay, that's it. Yeah, when you go deeper, suddenly you start to see a lot of things. Oh, I can do this, I can do that, right? Okay. For example, you want to do planning, investment. Yeah, so say you have a highway network, so you know the capacity, total demand is given. Yeah, efficiency the same, yeah, 75. From here, you calculate the maximum congestion, right? So under current demand, yeah, we want to reduce the maximum congestion, yeah, from 80% to 70%. Okay, so you want to increase the capacity. Then you can calculate, okay, how? Yeah, using NFI, yeah, network flow identity, yeah. So how to calculate? You just put it into the formula, isn't it? Because C2 equal to K2 divided by, yeah, the maximum congestion and efficiency, isn't it? Because you get all these numbers, okay, then you will get the new capacity. So what's the different capacity? Earlier was 25,000. Okay, the new one now become 28. So that means you minus this, you get 3,500. So that's if one lane is about 1,800, that means you need two lanes. Wow, interesting enough. Okay, look at this. NFI does not tell you which link you need to add the capacity. It just gives you the idea of macroscopic, yeah, strategic level. I know I need to add two lanes there in the network, but I don't know where. Okay, if you want to know where, you go to the ideal traffic assignment. Okay, so that you will be able to get the detail. You need to simulate, you need to optimize. Okay, but before going there, you need to check this first, isn't it? This is the first time, isn't it? Because if your idea is not worth it, it's not feasible, there is no use to calculate the detail, isn't it? Okay. Calculate first if your idea is actually feasible or not. Okay. Is this clear? Yeah. So NFI is the first step. Before you go to the detail, you must check this one. Right? So you want to go to the identify which link I need to put and so on. That's the detail later. Okay. Clear, yeah? I hope this help you to get the idea why this matter. Okay. So now having this, if you notice this, all of this, I divide, isn't it? I divide with the first scenario with the second scenario. Yeah. So in that case, why not calculate directly based on ratio? Okay. So NFI itself is useful. Okay. To get the trade-off, isn't it, between variables, right? Now, if I have two scenarios, yeah, the baseline scenario is at the bottom, okay, and then the alternative scenario in the top. Okay, so I can divide, right? Look at this. This is exactly NFI, yeah, the NFI value. Okay, so I just divide, and then now I separate per variables. Okay, exactly the same as NFI a while ago, but now I put it into ratio. Up to here, clear or not? What does it mean? NFI is absolute value. You need to know the actual demand. You need to know the actual supply. Correct? You need to know the actual efficiency. Yeah. And you need to know the actual maximum congestion. Using NFI ratio formula, this one is similar, yeah, similar formula. In here, you don't need to know the actual value. You only need to know the change. Okay, the percentage of change. Okay, so when I was in high school, I learned physics. You probably also learned the same, yeah? Physics. In physics, there is position, okay? And then there is the first derivative of position is speed. Okay? The second derivative of speed is of position is acceleration. Okay, so NFI is like the position. NFI ratio is like the speed, the first derivative. Okay, later we will go NFI sign analysis, that like the second derivative. Later, maybe next meeting, I don't know. Okay, so using NFI ratio, look at the formula is almost the same, but this is ratio now, the change. Okay, very, very useful, because now you don't really need to know the actual value. All you need to know is only the change. Very interesting. So, for example, I said the total demand the same. If total demand the same, all you need to do is to set this one become 1. Okay? So if you say, okay, the capacity the same, then this one become 1 also. Then suddenly you see R far pi is just 1 over R of maximum congestion. So now you get very simple formula. Okay? You see, like this. So now you see, oh, if one increase, the other one must be decreased. I can see that. Okay. Based on this, okay, you can also derive certain rule of thumb. Yeah, engineers want to do rule of thumb. Yeah, yeah. I created what is called queuing rule of thumb. Yeah, Q-rod. You can check in Wikipedia. So this one also, okay. If you know the network flow identity, yeah, you can also practically create rule of thumb to decide very fast. Yeah. Not necessarily correct, very rough, but you can decide very fast. Yeah. So at this point, we don't have the research yet on what is the actual typical far pi value for urban network. So this can become your thesis or dissertation, just to investigate this in certain values. Yeah. So it's a good topic, isn't it? To check your own cities. Okay. So while waiting for that kind of research, okay. So let's assume, yeah, because we don't know the actual value, let's assume, yeah, the worst case scenario. So let's assume I put it far pi is 25%. Maybe less, I don't know. But at this point, let's assume something. Okay, so that we can get certain numbers. Okay, so now if I set far pi 25%, now I want to do planning. Okay, say let's make the maximum congestion level typically 0.8, right? Maximum congestion level, say 80%. So now you use the NFI, okay? Because you know this one is about 1/4, the other one is 80%, so 4/5. You put it in, you get a new value. This is rule of thumb, okay? Not necessarily correct, okay? But at least give you certain numbers. hey, what does it mean? If I want to maintain certain maximum congestion, okay, then I need to put the total capacity is at least 5 times of total demand. Nice. Okay. Rule of thumb only, not necessarily correct, but at least give you certain idea. Okay. The same thing, yeah. If the total capacity and efficiency are constant, right? Then you say maximum congestion is proportional to that total demand, isn't it? So that means 10% increase in the demand, approximately the same percentage of increase in the maximum congestion. Logic. Yeah. Because on NFI ratio a while ago, now you can start to see this. Interesting, yeah? Yeah. So the same thing, if you want to improve the efficiency, yeah. So say the total demand and capacity is the same, right? So that means efficiency related directly to maximum congestion, going up and down is the trade-off, yeah. How much? The same exact percentage, yeah. Meaning 5% increase in efficiency will reduce maximum congestion by 5% also. Yeah, this is how you will say, oh, I need to invest in an intelligent transport system, yeah, traffic demand management, and so on. Yeah, because based on simple ratio, you can already guess, yeah, estimate how much. Useful or not? Yeah, very rough, but at least give you idea. Better than nothing, isn't it? Okay. Before this, you don't know, right? But now you know. At least this is the percentage, no? Okay. The same, if you want to target reduction of 5% in maximum congestion, then you need to improve efficiency by 5%. Isn't it? Okay. So the same. If you want to increase efficiency, yeah. So aim for higher efficiency by ensuring the balance of capacity. Yeah. So this is the way to do. Yeah. So one way to improve the balance is actually symmetric capacity. Yeah. Remember, symmetric capacity is always pragmatic. Yeah. Symmetric capacity is always pragmatic. Wow, that's simple. Yeah. So if you want the network to be robust, you need to create redundant route. Okay? You need to open up the villages that closing the gate. Yeah, this is phenomena, isn't it? So you keep closing the gates, so there is no other alternative. That means you actually worsening the situation. Okay. Okay. So oh, the rule is simple, the formula is simple, but when you go deeper on that formula, you understand the actual formula, suddenly, okay, wow, a lot of things I can do with this, isn't it? Okay, yeah. So if you want to have another example, yeah, what is estimation of maximum congestion? Well, if you know the far pi is 1/4, then you will say, look, that's exactly the same as 4 of the average congestion, yeah? So approximately, not necessarily correct, approximately. Okay, during the peak hours, yeah, you will see of the average congestion is about 4 times. Okay, the maximum congestion is about 4 times of the average. Yeah. Again, this is based on the assumption of 1/4 a while ago. So if you already get the actual value for your city, that will change. Yeah. Is it nice or not? Yeah. So if you want to compute the actual travel time, then you use the VPR formula. Okay. Then you can get the percentage, yeah, of improve in the travel time. Yeah. So simple. Okay. So the same thing, yeah. If you can actually track the FARPI index in your network, yeah, I don't know, maybe you use certain sensor, yeah, certain survey, yeah. If you can measure this FARPI index, okay, then you can trigger responsive measure, yeah. If there is some certain drop in the efficiency, you know, there is certain accident probably, there is certain traffic signal that adjusted manually by certain person, right? So monitoring the FARPI index is one way, yeah, to diagnose, okay, if there is certain problem in your network. Okay, so this is one of the application. So okay, this is the next chapter. Do you have a question up to here? Give me feedback. Come on. Interesting or not?
Interesting, sir. Very interesting.
Okay. So can you use this? Sure, right? Now, the next one will blow your mind. Okay. This is acceleration. Okay. This is sign analysis. Okay. Remember, using NFI, you need to know the actual value. Using NFI ratio, you only need to know the change. Right. Okay. But now, using NFI sign analysis, you don't need to know the actual value or the actual change. You only need to know the direction of the change. Wow. Okay. This is one step more aggregation. Yeah. So using NFI sign analysis, you don't need to know the actual or the change, but you need to know the direction of the change. Going up or going down or remain the same. This is more aggregate, huh? This is more macro, more strategic level, isn't it? Okay, so remember, yeah, if the NFI is like the state, it's like the position, NFI ratio is like the speed, the first derivative. So NFI sign is actually the direction of the change that's similar to acceleration, in second derivative. Yeah. So how do you define the sign? Okay, so I will write it as S, yeah, S means sign, okay? So the sign of X can be kappa, C, far pi, or C, yeah, these four variables, isn't it? So this one, okay, you just put positive, that means R, the ratio must be larger than 1, right? So increase, okay? If 0, that means the same as 1, yeah? The kappa does not change, for example, yeah? Or capacity does not change, okay? Negative means, yeah, between 0 and 1, okay? The ratio is between 0 and 1. Is it clear or not? So, now we have 4 variables, yeah? And then we have 3 states, okay? We have 4 variables, right? This one. And then we have 3 states, only minus, 0, and positive. So increase, decrease, or remain the same, yeah, invariance. Okay, in that case, the total number of possibility is 81. Okay, okay. So now I will give you name. Yeah. So when kappa is very important. Yeah, the total number of demand. If kappa invariant, the total demand is the same. So let's call this iso kappa. Okay. So when you have iso kappa, there is only 27 possible sign tuple. Okay. So out of these 81 possible sign tuples, only 51 sign tuples are feasible. Okay, let's go down at the appendix here. I computed one by one for you. So you don't need to compute anymore. Okay, I computed one by one for you. Which one is possible? Which one is not? Okay, so this is trivia. Yeah, there is no change in kappa. There is no change in this one. Yeah, capacity or invariance. Everything, of course, trivia. Yeah, and this one is not possible. So if you have certain policy, okay, say your boss or the certain politician telling something in the news, just check this one. Okay, increase or decrease, constant. Then you will see which one is feasible or not. If it's invisible, you can know that they are telling lie. Or maybe it's yourself, then you know, look, my idea is not working. Good or not? Mind blowing. Okay, this is the power of mathematics. Can you see that? Okay. Okay. So now out of these 81 possibilities, okay, only a few is actually called Pareto essential. And a few is called primitive. Now, later we will use this. Yeah. Okay. Okay. Let me explain a little bit. Yeah. So, what is the actual goal? The best goal is this one. This is called APEC, Pareto essential. What is the meaning? Look at this. Yeah. I will always use the same tuple. Yeah. Okay. I don't change the order. Okay. Always kappa first, and then C, and then far pi, and then maximum congestion. Yeah. C. Okay. So here, you want to increase the demand. You want to reduce the capacity. You want to increase the efficiency, and you want to reduce the maximum congestion. This is the goal of your policy. Okay. Yeah, that's why this is called APEC Pareto essential. Yeah, if you can achieve this, very nice. This is feasible. Okay. So say, but certain plan you don't want this. Yeah, certain plan you said no. I want certain things need to be constant. Okay, so there are certain things to be constant. Then you need to compute. Yeah, what is called Pareto optimal. What's the definition of Pareto optimal? Okay, here. Within feasible, this is the definition, yeah. Within feasible set, a sign tuple is called Pareto essential if and only if no other feasible tuple is weakly better in all 4 variables and strictly better in at least one. Okay, I give you an example so that you understand this one. Okay, so to compute that, okay, I need to run one by one. Say, kappa positive is higher than 0. 0 is higher than negative, right? For the demand, you want to increase the demand. Population always increase anyway. Economic is increase, so you want to increase the demand. Okay. But capacity, you need to reduce. So reduced capacity is better than zero, and then zero is meaning no change, yeah. And no change is better than increased capacity. Why? Because it's costly, yeah. To increase the capacity is costly. The same thing, efficiency is increased efficiency is better than no change, okay? And then reduced efficiency is bad. Okay, so the same, yeah. Reduce traffic on congestion, maximum congestion is good. Okay, no change. Okay, is second, and then increase of maximum congestion is bad. So now you can put numbers on this, yeah. So if kappa and efficiency, yeah, for pi, because the sign is like this, the same. Okay, then if positive, you keep number 2. Yeah, if no change, you keep number 1. Okay, and then if negative, you keep number 0. Like that, yeah, the same thing here. This one is capacity and the peak, yeah, the maximum congestion. They are the same ranking, the same order. So now the rank is now reverse. Okay, and then you compare, yeah, compare between two tuples, yeah. So if the tuples total of this ranking, if they are, you can say tuple A dominate tuple B if and only if, yeah, for every variables, yeah, 1 2 3 4, because 4 variables, right, the rank is always higher, and is important, yeah, at least one variable must be strictly higher, and not just this higher mean higher or equal, yeah, but one of them must be strictly higher, yeah. So if any of this rank actually lower, then it does not dominate. Okay, so let's say example, yeah, this one, plus minus plus minus, this is our goal, right? And then plus plus 0 minus. Okay, so you compare one by one, yeah. Kappa is plus and plus, so the same, right? This one is minus and plus. So because this is capacity, so better, yeah. A is better than B, yeah. And then for pi, okay, A is better than B, yeah. For maximum congestion, they are tie. Okay, so this means at least one streak. Yeah, that means tuple A dominate tuple B. Is it clear or not? Yeah. Anyway, this is just explanation how you compute. Yeah, but if you don't want to compute, I already provide the at the bottom and the appendix down there, so you get the result. Yeah. But if you want to test what I'm doing is right or wrong, so you can check one by one. Yeah, doing all of this. Yeah, comparing all the tuples. Yeah, 81 times 81. That's very big matrix. Okay, so you can also set one of them is no change. Yeah, so this is if the kappa, if the total demand does not change. This is if the capacity does not change, efficiency does not change, or the maximum congestion does not change. These are another Pareto essential, but have certain constraint here. Okay, and then I can also create what is called primitive. Yeah, the actual theory about this primitive is really rather complicated. I cannot explain here. Well, if I explain that will take one whole course on itself. Yeah, this based on convex geometry. Yeah, so but you can search this one. Yeah, convex geometry, extreme ray, convex cones. Okay, basically the idea is to create the chains, and then you take the logarithm of that, and then you put the ray, yeah, from the origin to certain thing if they are in the same plane, okay, or not, like that. Yeah, whether they create a cone or not. Okay, so that's how I computed this. Yeah, but I don't want to go to the detail on that. So this is the result of the computation. Okay, so we get only 12 of primitive. What is the meaning of primitive? That primitive mean based on this primitive, okay, you can create any policy of that 81s. Oh, of the feasible one. Okay. Based on the primitive, you can create any policy that you want. You can design your policy. Okay, let me give you example so that you understand this. We still have only 3 minutes. So, okay, this primitive can be you change the value. Okay, two change and then two constant. The second one is iso kappa. That means trade-off, yeah, between efficiency and capacity, or capacity with the maximum congestion, or the efficiency and maximum congestion, yeah. Okay, these are the value of the sign, and these are the ratio pattern. Okay, I will show you how you will use this, yeah. So this is the steps. Okay, number one, you set what is your policy that you want, target. For example, a plus, minus, plus, minus. Okay, and then you set certain demand ratio. Yeah, kappa is important, so total demand is very important. So you need to put the ratio. So I put this R, yeah. So, and then you pick up the primitive base ratio, yeah, based on that table. Here, this one. Okay. Okay. You pick up primitive base ratio. Okay, so this practically only three pattern, yeah. This pattern, or this pattern, or the last pattern. So you can pick one of them. Regardless which pattern you use, it will lead the same result anyway. And then again, you pick two iso kappa trade primitive. Okay, the technique is you pick two iso kappa primitive. This one. Okay, two. Now let's name it A and B. After that, you multiply this value and the two iso kappa. So you will create new ratio here. Okay, and then because you have the target here, okay, then you set up a constraint, and then you calculate the value of this lambda. Okay, then you will get exactly what you want. This is how you design the actual ratio that you want. I give you examples so that you will understand. Okay, so suppose you want this one. Yeah, this is the APEC, right? So you want increase the demand, reduce the capacity, increase efficiency, and reduce the traffic congestion. Okay, so say you get the base ratio, any of that a while ago, and then you pick two iso kappa, yeah, from the table. Okay, so based on this value, okay, you get the ratio value of that. So this is from the table. Yeah, this is the table that I already provide. So what happened is, yeah, now you multiply the three of them. So I will show you in this form so that you can see easily. So I have the base, I have the iso kappa 2, okay. Then I need to compute one by one. So R multiplied by 1 multiplied by 1. So still R, right? 1 multiplied by 1 over A, yeah, multiplied by 1. So still 1 over A, right? The same thing here. R multiplied by 1 and then 1 over lambda B. So you become the third one, this one. Yeah. The last one is 1 multiplied by kappa, lambda A, lambda B. So multiply. You got this? Okay. So now you have this value, okay, and you have your goal, right? This is the one that you set. So you can set any value. Yeah. This one, R must be positive, so that means larger than 1. 1 over A must be negative, that means less than 1. Okay? Okay? And then this one, R divided by lambda B must be positive, that means larger than 1. Okay? The last one, lambda A times lambda B must be negative, that means less than 1. Okay? So with that, now you can set, this is the one, once you have the constraint, you can set any value. For example, R is 1.1, so you increase the demand by 10%, then everything collapse. You can compute everything. Okay, that means, for example, here, if you want to achieve increase of 10% in demand, a 5% reduction in maximum congestion, you can still reduce the total capacity by 3% by improving efficiency by 19%. So you can design your policy. Is this useful enough? I know this is maybe very fast, okay? But please read this one. Yeah, there are several other examples here that you can start to see. Yeah, the last one is example that actually this is impossible, not achievable. Yeah, if you look at the appendix, this is not achievable. But you, assuming you forget to look at the appendix and then you compute by one, yeah, one by one, yeah, and then you will see that this is impossible. The constraint will tell you that this is impossible. Yeah, this is actually how we compute that appendix anyway. This is how you compute. Okay, so okay, in a summary, okay, so this is very powerful tool, isn't it? You can design your policy, yeah, and in the strategic way, yeah. So depending on what is your goal, you can set your goal, and it can also check the actual policy design, yeah, in the strategic way, yeah, not the detail yet. We don't know how to change. You only know what to change, isn't it? So this is the first step to do any optimization or traffic assignment and so on. If you cannot have that policy is actually feasible or not, okay, then it's not useful, isn't it? So I hope this is good enough for you. Yeah. So I hope you can also present like this. Yeah. Next meeting in your presentation for your group. Okay. To be reminded, one group did not submit the grouping name, so I don't know which one. So please submit. Yeah. Minus 1% per day deduction if you are submitting late. Okay. So read again this one so that you understand better, and then do the assignment, 2 assignments. Yeah. One individual, the one is group. So thank you very much. Sorry, a little bit late. Yeah, 5 minutes late. Okay, see you. I hope you enjoy this. Yeah, bye-bye.